Well, hello, my name is Tony Hines. I'm in the Department of Atmospheric Sciences, and it's a great pleasure to welcome Dr. Daniele Bortoli from the University of Evora. He's here as part of the Erasmus collaboration program. A number of faculty from Evora have visited Erasmus, and I should acknowledge Dan Suman, our colleague here at Erasmus, who has been the Erasmus lead in getting us involved in this program. At this point, Dan has been to Evora, and I'm looking forward to heading off to Evora next weekend. So, just to say a little bit about Daniele, he's, you can see a few things up on there, but he was actually born in Modena, Italy. Certainly one of my favorite places. I was there actually in June. It's the Motor Valley, very, very famous. Ferrari, Bugatti are all around there. So he has both Italian and Portuguese citizenships. Let's just see, where did he do undergraduate? So he did his undergraduate degree in at the Alma Mater Studitorium, Bologna University in 1998. And then completed his PhD in atmospheric physics at Evora University in 2005, and presently he's an assistant professor at the physics department. But you can see he's heavily involved in a whole number of international collaborations. Let's see here, just to he is a co-author of more than 200 articles, and he's involved in both instrumentation development. He has particular interest in LiDAR, but I think a whole variety of different things. So, welcome.
Thank you. Thank you, man. Thank you, Tony. I'm very pleased to be here, and I would like to thank Tony and all the people of the School of Marine Atmospheric and Earth Science to welcome me. And today I would like to show you something regarding our activity in Portugal, because I'm here mainly to learn and to understand if there is the possibility of collaboration between the University of Miami, specifically the Earth Mass, and the University of Evora, specifically the part of observations and modeling and development of new instrumentation. As you can see, I'm involved in many, and as already Tony told, I'm involved in many international collaboration. I forgot to put here all the cost action that are actions, project from the European Community, European Union, that foresee the network and the exchange of professors. I'm involved in 2 or 3 of these cost action. Harmonia, Probe, and another one that I can't remember the name. But anyway, and I would like to show you something before entering in the real the topic of the presentation, that is instrumentation and the Evora Observatory. Some word about the remote sensing, definition and operation mode of the remote sensing, the optical detection mainly, the applications that the remote sensing can have. And then I will show the Evora Atmospheric Sciences Observatory with its reference instrumentation, the development equipment, and the upgrades that are foreseen in the next years. And then the collaboration outside Portugal that mainly are infrastructure, or network, we are inserted in Actris, aerosol cloud and trace gases research infrastructure. The Propolar PNRE, that is, Propolar is the Portuguese Polar Project, and the PNRE is the Italian National Project for Antarctic Research. Then a profile that is something related to the atmospheric profiling, and also the microwave radiometer network that is now growing in Europe. So, remote sensing. What is the remote sensing? I believe all of you know what effectively is the remote sensing, but if I go, everyone now, when you want to know something, go to Google and to find the explanation of what they are looking for. The scanning of Earth based on satellite or high-flying aircraft in order to obtain information about the Earth. This is the Google definition, that is not really right, because in academic, effectively, the acquisition, the remote sensing is the acquisition of information of an object or a phenomenon without making any contact with the object. And this is in contrast to the so-called in situ observation that use a sample of air or of the medium that you want to study to obtain information about it. So, the Google definition, let's say that is a definition made by the satellite community. There is a satellite, you can see the satellite here. Satellite here that is making its geostationary satellite, so it is placed 36,000 kilometers from Earth to have always the same image of the Earth. And this is what the satellite community means with remote sensing. The remote sensing is not only that, not only from the satellite, but also from the ground. We can apply the remote sensing, and the remote sensing effectively is the detection and analysis of the signals that are reflected by the analyzed object after the interaction with the radiation. So we study the backscatter signal, the signal that is reflected by this object. And the remote sensing can operate in two different modes. There is the passive remote sensing, when the radiation source is a natural radiation source, in our case the sunlight, the sun, or the active remote sensing, when the radiation is artificial. For example, an halogen lamp or a monochromatic emitter, that a LED or a laser. And the remote sensing can be applied to very huge topics: atmospheric structure, composition, radiative transfer. You can see here all what are the application. The active remote sensing technique, inversion method, method for calibration, validation, and quality control. And this application can be used for ground-based and satellite remote sensing data for study of temperature, composition, aerosol, crowd properties, precipitation, sea surface, and sea ice. So the remote sensing can solve a lot of problems. And at the Evora Atmospheric Sciences Observatory, EVASO, in the south of Portugal, we have a lot of instrumentation. You can see here a view of the observatory, where Tony will be next week, maybe. And here there are the instruments that are mainly used for the detection, for the study we are accomplishing. And now I will show some of these instrument that I saw in the last day I was here that some of them are also installed here. For example, this is a photometer, a spectrophotometer made by Sinel that we have two of these in Portugal, and also here there are two. I saw last day that there are two of these that are measuring. So also Miami is aeronet station. You can see a lot of stations. Effectively, aeronet, the aerosol robotic network, is born in the US and then spread along over the world. And with this instrument, we can determine the aerosol optical depth of the aerosol particle or aerosol, the column water vapor concentration, aerosol dimension, and these instruments are really old because it's working there since June 2003. Then we have here, you can see some example of what we are able to retrieve with this instrument. The Armstrong exponent and the effective ray of the particle. Then we have infrared radiometer, a number here, I put here one for example, because we have infrared visible and erythemal radiometer installed there. And they are all old instruments because you see 2002. Also this is a sun radiometer, it is a broadband radiometer from 285 to 2080 nanometers, and this is for the diffusion of elements. You can see this is a manual, almost manual instrument because we have to change the position of the shadow band each 15 days, 1 month, because we have to follow to be sure that the shadow cover the sensitive part of the radiometer. Then also this, I saw that there is one here that is working. This is a spectral radiometer, MFR set multi-filter radiometer. With the 7 is for the 7 channel, and it used for the detection of aerosol optical depth, column water concentration, aerosol absorption, and aerosol chemical composition. And you can see here, this is 2017. Yes, it's a plot, a daily plot. For example, as an example in 2017, and you can see here this was really a clear and cloudless day, but you can see that there are some points that are outside the normal, the expected shape of this of the curve, because these are not clouds. Usually these happen when there are clouds. Instead, these are obstacles that are in the middle of the field of view of the instrument. So we know when we made the processing, the data processing, we know that in this place there is a problem and we have to take care of that. Then we have also a Skycam camera for cloud cover assessment. This was built by me and a colleague of mine in 2013 and is there working since then. It takes measurement, it takes photos each 5 minutes, and then these photos are sent to to a site, to a computer where are processed, and you can see here, for example, the cloud cover today. This is today. I made this slide some minutes ago, so it's completely working well. There are some clouds there, and these are reported in this options. Excuse me. I don't know if you are able to see now. Anyway, this is, you can see in this plot at the bottom, you can see the temperature here in Evora that is rising. Is not 75 Celsius degree, but 57 Celsius degree is the temperature inside the camera now. So it's really warm there now. And then this is the Skycam was an experiment that we made some years ago, and we developed this Skycam. And then I developed with a colleague, with my chief in Italy at the time, we developed this spectrometer for atmospheric traces measurement that is based on a spectrometer, an optical layout that already was done in the 90s by a group of the Institute for Atmospheric Sciences and Climate in Bologna, in Italy. And this is a spectrometer for the observation of diffuse solar radiation at different solar zenith angle, and for different solar zenith angle, and for different elevation of the input of the radiation. This spectrometer can measure from 300 to 600, no, to 1,000 nanometer, 1 meter. And in following windows of about 60 nanometer each. This is obtained rotating the grating and to have an higher spectral resolution that can be used after for the detection and for the assessment of the trace gases concentration. But before that, here there are all the steps of the construction, and I can explain, or better, it can be seen that how it works. The spectrometer, the light enter this spectrometer with enter the spectrometer with this kind of input, rotating input with a mirror, and then the light is focused on the slit where it enters. The slit send the radiation on a grating. The grating made the dispersion, and it make dispersion in the different wavelength, and then another mirror send the radiation over a CCD camera where there is a CCD sensor of 1024 times 256 pixels, and this can be then this measurement, this image is sent to a computer for storage. The important things of the CCD sensor is that it is cold at 40 degrees, minus 40 degrees of temperature, to have a very high signal-to-noise ratio. This is mainly the mechanical, the electronic part that is used to control the the instrument, all the device in the instrument. In the instrument there are at least 4 stepper motors that can control the position of the grating, the position of the input mirror, and the position of 2 filter wheels with interferential filter and neutral density filter. And you can see here all the connections that are schematized here. I did I know every cable of this instrument, and this is the schematic that can summarize the connection. So we have an industrial PC, the PC Nova, that is controlled by different that controls different relays through a relay optical interface that I developed some years ago when I did the instrument. And then there are the ROI control 4 or 5 relays that are switched on off the mercury lamp and the halogen lamp that are used for spectral and radiometric calibration respectively. Then there are the Peltier module and the fan for the Peltier module. The Peltier module is used to maintain the temperature of the instrument inside a working range that usually is about 20 degrees. This because the variation in temperature can cause different mechanical stress, so the parameter, the dispersion parameter can change, and the measurement then has to be correct. And to input, at the beginning it was a telescope outside with a optic fiber that was taking the measurement. But I wanted to be more precise with that, so I developed this alt-azimuth platform that can be used, and it's used to make measurement for different elevation of the input. And this allows to also to apply another methodology that is quite new. It's 20 years that this methodology, this variation on the differential optical absorption spectroscopy is born, and is the MAX DOAS, the multi-axis DOAS. This allows to have vertical distribution, not with a resolution of 2.5 kilometers as it is when I watched only at the zenith sky, but of about 250 meters in the troposphere. So this is a big advance of the Max DOAS technique. And to manage the instrument, I implemented this program, this software that can be used to test all the parts of the instrument. You can see here the mirror grating, filter, calibration, out range. There are a lot of functions that can be done, but it can be used also for the automatic measurement. For example, I have an instrument the instrument that is installed at Evora since 2004 is measuring from there. Besides some problems that I had, is always continually measurement 24 hours per day, and it's a great result. But what we do with this, what we measure. So here you can see the scattered radiation in 4 different, for example, in 4 different windows that can scan the spectrometer from 300, 370, 350, 420, and 400 various different windows, and I can identify in this spectrum spectra, the Fraunhofer line, for example, between 350 and 420 nanometer, I can identify the K and H Fraunhofer line that are mainly due to the calcium. And this is how is installed the spectrum there. This is another piece, the telescope. When I was talking about the fiber is inserted in this telescope that is it's called VELOT, vertical looking device, because it's looking only at the zenith sky. And these are some results obtained with the spectrum compared with the OMI, ozone monitoring instrument, that is an instrument installed on satellite. And these are the ozone vertical column density, so the total column of ozone for 2, 3 years, 4 years, and you can see that the shape is the same, the behavior, the annual behavior, the seasonal behavior is respected. There are some difference, but it has also to be considered that the OMI is installed on a satellite at 700, is flying at 700 kilometers, and then also because these are points that are obtained during the overpass of the satellite, that is around 13:30 local time. Instead, the red data are daily average of what measured by spectrum. And these instead are other results, mainly the full time series is stopped in 2022, in July 2022, the last time that I ran everything to see how it was working, the instrument. And this is nitrogen dioxide for solar zenith angle of 89.5, 90.5, so at sunset, at sunrise. And you can see that it's clearly visible the photochemistry activity of NO2, because the blue lines, the blue points are the obtained result for the sunrise. So in the morning, when there is the nitrogen dioxide concentration is lower, abundance is lower, and the orange points instead are for the sunset. So during the day, the photochemistry act and create the energy. I can also tell something about, no, I don't want to tell something about the trend, because during, I can see a trend, the total trend, the trend of the total data, of the full data set, it seems to be positive, but effectively I made some exercise for the first part and the second part of the data set, and I saw that this is an artifact due mainly to maintenance that were done to the instrument. So it's like that. But how this result has obtained? So here there is a really condensed workflow of the differential optical absorption spectroscopy that can be seen as the measurements, the first plot on the left, the measurement. I have a measurement at sunset, a measurement at sunrise, and the measurement obtained at the local noon that is considered as the reference spectrum. Then the reference spectrum, the logarithm. Then with the reference spectrum and this cross section differential cross-section of the different compounds that has absorption in this spectral window, I can build this equation, that is the master equation for the DOAS, that is a variation of the Lambert law, extinction law, and then with this superscript on the second term of the equation, this is the mean function that will be subtracted to the logarithm ratio of the two spectra, the reference spectrum and the analyzed spectrum. In this way, I obtain a match, the best fit from the logarithm ratio spectra of the measured spectrum and the cross section, and I will obtain the concentration of the Slant column, the concentration along the path of measurement of the analyzed compound. In this case, the first is for NO2, the black line is the NO2, and the bottom plot instead is for ozone in different spectral windows. With this, I can obtain the slant column density or vertical column density applying the Hermann's factor, the geometric factor to correct for the vertical, and then with other numerical inversion, I can obtain the vertical profile of the compounds analyzed, in this case, NO2. And these are only the software I developed to obtain the data I show you before, and you can see here more or less the same figure, the same plot that I showed in the previous slide. The problem with this software is that when I started to do that, I was young, so I had no very knowledge of the programmation, so now it's very, very slow. So I passed to another software that is made by the BIRA, by other group that use DOAS, and this can be used, and is very, very fast than the other. And we have here some place where this sputter, because I did not build only one of these instruments, I built 10 of this. I finished last week the wiring of the last one. And we have here, we have in the south of Italy, in the north of Italy, we have one that was in Sicily, one in Spain for a campaign. In Portugal it's always active, and we would like to put one also in the Azores Island and maybe not. But we have to wait for that. Coming back to one is installed, one of these instruments is installed also in Antarctica. Or better, there are two of the instruments. His grandfather and the instrument developed. And the Italian station, as you can see, is the one Terranova base station that is here in the Ross Sea. On the ocean. I'm not able to. You can see here. Yes. With the arrow is better. This is the Italian station. We have also here another Italian France station, that is Dom Concordi, Dom C, and all the other stations of the other. And this is the instrument that is installed since '95 at the Italian station. It's made more or less, is simpler, very, very simpler than the spatran or similar instrument, but it made the same things, and we have I show you here a comparison with GOME, Global Ozone Monitor Experiment, and TOMS, Total Ozone Monitoring Spectrometer, that is an American instrument. In 2002, it was many years ago, but it was an experiment that was done in 2002. I made the processing in 2002 because it was a period with a strong ozone hole that you can see here in the Austral spring. There is a big ozone hole detected by all the three instruments. Ozone hole, it's usually when the ozone fall down the 150 Dobson unit. And this is the full 2021. The last year is missing, but this is the full data set of data obtained with the old instrument in Antarctica. And this instead is the new instrument that is installed in Antarctica. You can see here the Altazimuth platform, the multiple input geometry equipment called the Valor that is here. Here they are installed with this long chimney, and this they are a little bit high because the snow here it can fall down a lot of snow and can be everything can be below snow. This installation was possible thanks to the Propolar project, the collaboration with the Isaac Institute, and the collaboration with the Italian project for Antarctic research. Coming back from Antarctica to Evora. Here there is the LiDAR that we use in Evora. The LiDAR that we use in Evora is a Raman LiDAR built by Tropos. Tropos is an institute of research, atmospheric research in Germany and in Leipzig. And this is the instrument how is installed now in Evora. The instrument works 24 hours per day, giving results for particle distribution in the eye, and we can see that it's composed of it has the emitting part is normal, almost normal, because the laser entered the laser beam entering a second and third harmonic generator, creating the 532 and the 355 wavelength. The laser is emitting at 1064, so we have these three wavelengths that are emitted, pulsed at 20 Hz in the atmosphere, and then the backscatter signal is obtained by this Newton telescope. This telescope that send the signal inside the optical part, where there are a lot. There are the PMT for the three elastic channels, 355, 532, and 1064, plus a channel for the cross-polarized signal, 532 cross, and then there are two more channels, 387 and 607, that are the Raman channels that are used for in the application of the track method of the Raman method. The other is for the track. Okay. And this is a photo of what's happening of the laser. And on the right, you can see here a plot of the range corrected signal of the obtained measurement, and this line at 16-17 kilometers was white, are the smokes coming from the Canadian fire in 2017. Yes, in August 2017. And it was one of the first places in Europe where we saw this event. That was, after that was detected also by all the other laser LiDAR station in Europe. And there are a lot of these instruments around the world, I would say, but only 6 are permanent station, and Evora is one of these permanent stations. And all the data are sent to the server of Tropos, and we can see the data of all the instruments that are working. We can also check the instrument, the performance of the instrument, and pre-processing. There are a lot of pages in this site where we can see the status of the instrument. This instrument, this kind of instrument, belongs to the aerosol cloud and trace gases research infrastructure. Or better, before there was another network that was the ERLINET network, European Research LiDAR Network. But then this ERLINET was absorbed, let's say, even if it's still present as a unique organization in Europe, was absorbed by the Aerosol Cloud and Trace Gas Research Infrastructure, but it's spread all over Europe. Here you can see the various stations that were used for an experiment done some times ago in 2019-2020 during the shut-off due to the COVID-19. And this is one of the tropospheric observation done in Evora in that time. So we have here a lot of things to do and to publish, you can see. But we have also this instrument that is a microwave radiometer that made vertical profile of temperature and humidity. Practically, this is the replacement of the meteorological balloon. The problem is that the meteorological balloons would reach the 20, 25, 30 kilometers. Instead, this one is limited to 10 kilometers of height. But for some studies, this is enough, and it costs something because it's a little bit expensive. But after a while, you can recover your money because you don't have to launch every 3 hours to launch a meteorological balloon. So, and you can see temperature, humidity, liquid water path, integrated water vapor, and is based on the microwave radiation into bandwidth. Okay. And this is what is recorded, what we can obtain with this instrument. The temperature, liquid humidity, liquid water profile, and this is a thermoline, than other things. This is one plot of the other plot that can be done with this software. And also here, also for this instrument, there is a network that is growing now, and you can see that in Europe there are a lot. Europe and South Asia, there is a lot of this instruments, and also in the US they are starting to appear. Finally, centimeter by CR31. This is a low power LiDAR that is used mainly for the cloud-based detection. It's a centimeter for the ceiling of the cloud. Every airport has one of these, not the CR31. Now there are more of this type, CR61 from EVASO, CAK. There are many of these instruments. And also this instrument that can be used not only for the cloud ceiling but also for the characterization of the backscatter of the particle, of other particles, not only clouds. And also for this there is a network that we joined some weeks ago, that is a profile, that is a network managed by the European Meteorological Network, and the responsible is the Meteo Swiss. And you can see that there are a lot of stations in Europe. Main stations are in Germany. There are a lot of stations. Germany was able to convince all the airports to share their data. In the other places, didn't happen, so it's quite difficult to access the data from the airport. And now, this is a summary of what we do with the remote sensing at the EVASO, at the Evora University, because we use satellite, MODIS, Calypso, Sentinel, Eros. We use ground-based instrumentation, microwave radiometer, ceilometer, CML, air quality station. I didn't tell you about that now, but I will tell you in a while. Those spectrometer, Raman LiDAR, who have hexacopter, I forgot to put this, and we have also seismic station, but this is for the part of digital physics, not the seismology, not the part of the atmosphere. And this figure is the presentation of the EARTH lab, the Earth Remote Sensing Laboratory, that is something that is growing also at the University of This is not important. Till now, remote sensing. And what about the in situ measurement? We have also something about in situ measurement. In situ measurement, the nepherometer TSI 3663 for the in situ measurement of various dispersion coefficient in 3 different wavelengths, in the blue, in the red, in the green. That is working a lot of time. Then we have this APS, aerosol particle size spectrometer, that is also working there for a lot of time. So we can use data also from the in situ instrumentation, and these are most of the instruments that I take care of. And then we have this multi-angle absorption photometer from Thermoscientific, that is for the black carbon. And then the TSI optical particle sizer. This is an optical particle sizer, a portable one, but I was able to put this also working continuously, is online 24 hours a day. Then we have this tapered element oscillating microbalance at the home series. that this is fantastic because there is a small filter that is installed in something that is vibrating very at a given frequency, and when the particle deposited on the filter, it is possible then to obtain the mass of the particle deposited with the analysis of the variation of the frequency that is called. And then we have also this, that is the caravan for the air quality measurement. The air quality measurement done with the analyzer of SO2, ozone, nitrogen oxide, that is this analyzer here. On the other side of this column in the caravan there are other instruments. Another instrument that is there is this one, that is a beta gauge monitor. The instrument is done. This is the synoptic screen, but the instrument is done exactly like that. There is this optical module that can distinguish between PM10, PM2.5, PM1 particle, and then there is this part below with this filter strip where the molecule, the particle are deposited, and then each half an hour, I believe, this module can rotate, and the green part that is a beta radiation emitter goes here, and there is a Geiger counter below that can count the radiation, measure the radiation, and with differentiation of the radiation I can know the particle, the mass of the particle deposited on the filter. Yeah. And these are a graph, a plot obtained there, where you can see the PM10, CPM is the PM obtained with the optical module, the periodic concentration and the cyclic concentration are the periodic, the half an hour concentration, and the periodic, the 24-hour, the cyclic, the 24-hour concentrations. To maintain and to develop this kind of instrument, we have some of this, some facility, laboratory for the calibration, for assembling and calibration of this instrument. And these are the publication that we had. I participated in the last year, the last 6 months. So important. The first are all about LiDARs with international partnership. The last two are more important for me because this one is the highlighted one is a thesis of a student that made a portable measurement device based for determination in water of ions. So it was a low cost device, a low cost instrument that we were able to develop. He made a great work for this. And the last one instead is a paper on Doer's observation that I'm very proud of that. Also because finally, after I believe 7 years that was installed the instrument, some data went out. This was possible because Paolo Pettinari, the first author, is a PhD student, and without the PhD student, we are not able to do half of our work. I believe that it is very important to have students to work with because they have new open mind, and sometimes they are able to see something that we are not able to see anymore. And finally, I finished. Thank you.
Thanks.
Questions?
Is there anybody on Zoom? Can you tell him wants to ask any questions?
Yeah, there's only Lev Looney. If he has a question, he can turn his microphone on.
One question in the DEVAS focused on ozone and NO2, but I did notice bromine monoxide was actually mentioned on the slide. Have you made any measurements of bromine monoxide?
Yes, I made measurements, but the bromine monoxide is not so as an absorption, a weak absorption in this in the spectral window value. I made some years ago and have a publication, a conference proceeding regarding bromine oxide, but I didn't follow the curve. It's one of the things, one of the components, because I'm focusing on NO2 and ozone because they are relatively easy to detect. But I want to detect, beside the bromine oxide, I have to try also with the formaldehyde, that is also a big absorber in that in the first piece of 400-460 spectral range, and then SO2. I was able also to see SO2, but not reported here. And I didn't show all the, because there are I have 100,000 of plots of this and tests of this processing data. So.
Well, it's an enormous amount of work. So thank you very much. And
I hope that this can increase our collaboration, because if, as you propose, to send some instrumentation there for the mercury measurement, that we would like to start with that. It's missing from all this measurement. The mercury is not present, so I wanted to try also with that, and to have the possibility to make exchanges in this sense. For example, I don't know if here the differential optical absorption spectroscopy is used or not. I would like to see, and I would like to know if there is a possibility to install here something like that, because it should be really interesting. And as I was telling, by chance, I finished last week to make the wiring of an instrument. So if there is the possibility to have this exchange, mercury in situ there, and trace gases remote sensing here, it should be really amazing. We have to find the possibility. Yeah. Okay. Thank you.
Thank you very much.
Thank you.